Okay, perfect.
Okay.
Hi, guys. Good evening, everyone. I welcome all of you to this deep learning revision session. And this is one of the first sessions that we are having for Quiz 2. And for this session, we have our dear friend Pulkit. He's currently the TA for deep learning course. So, Pulkit, thank you for taking the session, and you may take over now.
Okay. Sure. Yeah. So, hi everyone. So, what I planned for today is basically I will be going over some of the topics from week 5 to 8. Okay. These are some of the topics that I feel that are important with respect to your quiz exam. Okay. Then I have few questions with me from the past year papers. So, uh, concurrently, we will be solving them also. Okay. So, a little bit theory, then moving on to the question. That's what I was planning to do for today's session. Okay. Yeah.
Yeah, fine.
So basically week 5 we'll start with. Okay. Now till week 4 the story was that we have seen how we move from our traditional ML methods to the deep learning model. Then started with the MP neuron model, then perceptron, logistic regression, then logistic regression. Then in week 3 we move on to finally to the artificial neural network part and the backpropagation method for that. And then in week 4, we move on to the optimization methods. For week 4 and week 5 together basically is only dependent on your optimization methods. Optimization methods is basically the improvements on the vanilla gradient descent methods that we had. Okay, because the standard vanilla gradient descent had some problem, like it will be expensive for computing the gradients for the entire data sets and all. So we will be basically studying the variants of different gradient descent algorithm exist here. Okay. Week 5, there are many algorithms, okay, but few, only few which you should specifically pay attention to are like your Adagrad, RMSprop, and Adam. Okay, these three are the important one, and the SGD and the vanilla gradient descent carries over from your week 4. Okay, so I'll be starting with the need of adaptive learning rate, or what does it mean? Okay, so adaptive learning rate basically means uh, that suppose you have some your loss curve like this, okay, then while doing your gradient descent, what might happen that your uh, uh, while iterating through the gradient descent, you might stuck at some local minima. Okay, now how you can come out of that local minima is it depends upon your learning rate. If your learning rate is very high, okay, then the speed with respect to which you will move will be very high. If your learning rate is very low, then the speed with which you will move is very low. Okay. Now it depends upon the path how the gradient will be. If you have a path something like this, it's a very steep region. Okay. So the wherever there will be steep region, the gradients in that direction will be high. Okay. So if you are going to set very high learning rate for this specific reason I'm talking about, where the steepness is high, okay, and because gradients are also high and the learning rate is also high, so the movement will be very fast and it is likely that you will overshoot your local minima or global minima. Okay. So for the reason where you have more steepness, you would like your learning rate to be a low value. While on the other hand, if you have some region like this, okay, it's kind of like a plateau region. Plateau means like a plain field region type. Okay. Now in that the gradient value will be close to zero, because we know that gradient, if you imagine it in like a one just single variable case, then if you have the surface area parallel to the x-axis, then gradient becomes zero. Okay, so if you have a surface which is like a plane field type, then the gradients will be very low, or you can say close to zero. So in that case, you would like to move very fast, or you would like to have a strong force to come out for that reason. So in that, in those reasons, you would like your learning rate to be a high value. Okay. So depending upon the path where you are, you would like either your learning rate to be high, when you are in plateau region. And if you are in very steep region, you will like your learning rate to be low. Okay. So this is the need for adaptive learning rate. Why we need the learning rate to be adaptive? We need it to be with respect to the region where we are. Okay. So our algorithms that we are going to study in week 5 are mainly focusing on that part. Because whatever we have studied till now in week 4, like your stochastic gradient descent, mini batch gradient descent, momentum gradient descent, or Nastrov accelerated gradient descent, these does not care into the account for your adaptive learning rates. Okay. So in that field, the first algorithm that comes is the Adagrad. Okay. So mostly things that you need to remember from week 5 is their intuition, how they works. Okay. And if they have any pros and cons regarding any algorithms, then that's what you have to remember. Most likely every term they give the formula. Okay. So you can also hope that this term also they are going to give you these formulas for update rules. Okay. But if you want to be safe, you can remember them also. Okay. Now the update rule for the ADA grade is basically this. It's basically have a vector which corresponds to the sum of squared gradient. Okay. So gradient at WT denotes the gradient. You are doing the square of it. Now remember here the square that is happening is element-wise square. Okay. By that I mean if like your gradient of W is something like let's say 2, 3, 4. Okay. Then gradient of W square that I'm writing here is basically 2 square, 3 square, 4 square like that. Okay. Element-wise square you will do. Okay. So it will first have a vector which basically accumulates your squared gradients. Okay. Then the update rule says that WT plus 1, the new updated vector is WT minus the eta, that is my learning rate, initial learning rate that I'm going to set, divided by the square root of VT. VT is this vector that I'm carrying here, plus some epsilon quantity. Epsilon, we set it some closer to 0 value so that we did not encounter any division by 0 error. Okay, this is just for computationally uh, handling. Okay, then multiplied by the gradient of WT. Okay, that's my uh, update rule for the Adagrad. Okay, now let me expand this recursive equation for you. We start with, sorry, we start with the initializing V naught to be the gradient of W naught square. Okay, so let me carry forward that part here. V naught is gradient at W naught square. The underscript basically denotes the timestamp. Okay, then V1 would be what if you follow the formula here? Okay, it's Vt minus 1 plus gradient at Wt square. Okay. So the formula for Vt is Vt minus 1 plus gradient at Wt square. So V naught is gradient of W naught square. Generally, we take V minus 1 to be 0. Okay, so that we can start off directly here. Because if you put V0 here, then V minus 1 is 0 and then gradient of W naught square. So V1 starting with is V naught plus gradient at W1 square. Our V naught is this quantity here. So it's just gradient at W naught square plus gradient at W1 square. Similarly, V2 would be nothing but gradient at W naught square plus gradient at W1 square plus gradient at W2 square. Okay. Similarly, for any Vt, if you are going to calculate for, it's gradient of W naught square plus gradient of W1 square, the square. Okay. That's what your velocity vector here is. This Vt is generally called as the velocity vector. Okay. Now, at any instant for which you want to update the value, you are just going to take this Vt and feed it here in this formula here. Okay. This is simply or similar to what your vanilla gradient descent formula is. It's just that here we are dividing our eta by this factor, square root of Vt plus epsilon. Okay. Any doubt here? Okay. Now, the problem with the Adagrad.
Hello.
Yeah, yes.
Hello.
Yes, yes.
Here I have a question that
Hmm.
how it's helping to, overcome that issue that was occurring. That's why we use adaptive learning.
See, the learning rate is changing, right? See, if
Hmm.
your gradients are high, Okay.
Mm-hmm.
If your gradients are high, then this value will also be high, right?
Mm-hmm.
Okay. Then the eta would be what?
Yeah.
Divided by this magnitude factor, right? So it
Yeah.
will become lower, right?
Small.
Okay.
Yeah.
So the thing that I talked about, that if you are in steep region, you would want your learning rate to be small. It is doing that.
Mm.
Okay.
Yeah.
But
Okay.
there's
No.
this problem here, that is
Mm.
this function that you are seeing. Okay. Now, can you tell
Yeah.
me, is this function monotonically increasing, monotonically decreasing?
Yeah. It's increasing. It's increasing because
Increasing,
we
right?
are squaring now.
Yeah, we are squaring, so
Yeah.
every element here is basically positive, and
Yeah.
you are doing the sum of that, then this quantity will always keep on increasing or basically stay constant if the gradient doesn't
Yeah.
become zero. Okay.
Mm-hmm.
So what will happen in that case? Your learning rate will become smaller and smaller.
It's
Okay.
smaller and smaller. Yeah.
Then later, if it happens that you encounter any plateau region, now in that region, what you would want your learning rate to be high, but that will not happen.
Mm.
Okay.
Yeah.
So
That's
this
the
is the
disadvantage of this
yeah,
Adagrad.
this is the advantage of Adagrad, that if your gradients becomes very high initially, or you get very high gradients in the starting, okay, then your learning rate will become smaller very fastly. And then later, if you need the high learning rate, then that won't be possible in the case of Adagrad. Okay. So one quick point for Adagrad is
Yeah. Okay.
the learning rate for Adagrad will keep on decreasing or stay constant if the gradients become zero in the later iteration. Okay, that's the key point for our Adagrad, and that's its disadvantage. Okay, now rest all is the mathematical computation. I have some question that we are going to do after I finish the week 5. Okay, but mostly these questions generally comes directly formula based, so you should not be having any problem. Okay, if Adagrad is clear, shall we move on? Okay. Now RMSprop, that's account for root mean squared propagation. Okay, its intuition is basically it's try to solve the problem that Adagrad had. Okay, so it's again used the squared gradient sum, but it's used a clever way of using the accumulation here. That is by some beta factor. Okay, so this is basically called as the exponential moving average in general, or exponential moving squared sum here. Okay, now I will explain it how it helps us. Okay, but just you can look at that only place that we change from Adagrad to RMSprop. It's just that in the Adagrad we did not have this beta term here, beta and 1 minus beta, while in the RMSprop we had this beta and 1 minus beta term here. Okay, the update rule for later our variable is technically same, that Wt plus 1 is Wt minus eta by square root of Vt plus epsilon times gradient of Wt. Okay, now let's expand this equation that we had here for Adagrad, RMSprop. Okay, now for the RMS prop, we had the equation is Vt equal to beta times Vt minus 1 plus 1 minus beta times gradient at Wt square, right? Yeah. Okay. Now again, our initial things will be same, that V minus 1 is 0. Okay, so if you put V minus 1 to be 0 here, you will get V0 to be 0 plus 1 minus beta times gradient at W naught square. Let's start with V1. V1 is beta times V naught plus 1 minus beta times gradient at W1 square. Let me replace my V naught here with this value. We'll get beta times 1 minus beta times gradient at W naught square plus 1 minus beta times gradient at W1 square. I can take 1 minus beta here common. So I will get beta times gradient at W naught square plus gradient at W1 square. This is my V1. Similarly, let me try with V2 is again using the formula, it's beta times V1 plus 1 minus beta times gradient at W1 square. If I replace my V1 here with this value and beta 1 minus beta times gradient at W0 square plus gradient at W1 square plus 1 minus beta times gradient at W1 square. Okay. Now you can expand this equation and try to simplify that. What in the end you are going to get is something similar. 1 minus beta times beta square times gradient of W0 square plus beta times gradient at W1 square plus gradient at W2 square. Okay, now let's stop it here and tell me, have you seen this inner form somewhere else? In any previous week, in any previous algorithm, this inner form.
Linear combination.
Not linear combination, something, a place where we also use our beta. Okay, we make use of that, and there also if you are going to expand the equation for later terms, you are going to get something similar. Okay, let me give you the hint. It was in week 4. Okay, so this was for momentum. Okay, in the momentum gradient descent algorithm also, if you are going to extend the velocity vector equation, this is what you are going to get there. Okay, for any vt you are trying to find, okay, in the momentum equation also you are going to get beta power t gradient of w naught. Just only thing that you are not going to get the square in that case. Okay, but here it will be square plus beta power t minus 1 gradient of w1 square, so on. Then beta power 1 gradient at wt minus 1 square plus gradient at wt square. Okay, and just that you are also going to multiply it by 1 minus beta factor. Okay, so this is the expansion form for our velocity vector here. Okay, whatever timestamp t you are trying to find your velocity vector, start with that power t for beta, multiply with w naught square, then just subtract 1 minus of power and w1, and it will be beta power t minus 2 gradient of w2 square, so on, beta power 1 gradient of wt minus 1 square, and for the current one we are not going to multiply it by beta. Okay, and this whole thing has to be multiplied by 1 minus beta factor. That's the expansion for this. Okay, now how does this helps us overcome the problem for our problem that we had for the Adagrad, that the learning rate keeps on decreasing. Okay, now if you look at this equation, okay, yeah, one thing I forgot to mention here, that beta generally belongs to somewhere between 0 and 1. Okay, now if beta is a quantity that is between 0 and 1, and if you are going to put it some power of, let's say, 10 or something, okay, then it will become very low, right? Okay, so what will happen in the case of RMSprop, as you move ahead in your iterations, okay, the previous histories of gradients will get very less weightage. Okay, because this beta power t minus 1 will be very low quantity. After some iteration it can become like close to 0, so we can even ignore those terms. Okay, while for the current gradients that I had, okay, then for the current gradients it will be having more weightage to it. Okay, so it's kind of like a sliding window thing. Okay, so like you are going to start with your w0, w1, w2, w3, 4, and so on. Okay, so RMSprop works kind of like a sliding window. Okay, I'm not going whatever I'm writing here, it's not going to be like kind of exact that you are moving with the frame of 2. Okay, I'm taking this as an example that you are kind of moving with the frame of 2, but it's something similar to that. Okay, it's like you are first putting focus on these two, then You're going to put more focus on these two because the previous part will be getting less weightage. Okay. Then the later two, then the later two, kind of like that. Okay. So it's kind of like a sliding window. Okay. The past gradients history will get very less weightage and the current one will get high weightage. Okay. So the problem that the Adagrad was facing, that the learning rate was keep on decreasing because the velocity vector there we had was continuously increasing. But here it need not to be the case because based on the current gradients value, it depends. So the learning rate can increase, can decrease, or it can remain even constant too. Okay. So everything can happen in the case of RMSprop. Yeah. Is it clear? Okay. Yeah. So that's what we have. Now, one problem that we had for RMSprop was that if learning rate become constant, okay, because if some iteration point of time that we do not get any kind of much boost for our gradient, then the learning rate can become constant. Okay, so constant learning rate can be painful because you can have the situation when you can oscillate in the case of constant learning rate. So this example that sir gave in the lecture was that suppose if you are at some parabola situation, you are at this place, and if your learning rate with multiplied with gradients throws you here, okay, but then again in the next iteration you come here, so this is the oscillation. Okay, this case happens when you have a constant learning rate. Okay, so that's kind of like a disadvantage you can think for RMSprop, that if the learning rate become constant, then it can oscillate. Okay, now the only solution, or not the only, there are two three solution for the constant learning rate. The other solution mainly include to warm stop or cosine annealing learning rates and all that we studied in the week 4 part. Okay, in the scheduling learning rate video, I think it was there in week 4 or either in week 5. But basically one way we can encounter the constant learning rate was setting initial learning rate carefully. But of course, because learning rate is an hyperparameter that depends upon our trial and experimental thing. Okay, so it's a very tedious task to do. So the next algorithm that we had in our list was the adaptive delta. Adadelta is it is called. Okay. I'm not going into the formula for the Adadelta as it is a little bit complex and it's not or never asked in the exam. Okay. So I'm just going to give you the intuition that it had or the main thing that it carries. Okay. The adaptive delta or the Adadelta algorithm is basically helps us setting initial learning rate. Okay. So in this algorithm, you do not have to define your initial learning rate at all because the way this algorithm works is in this 5 stages. Okay. So it make use of this history vector just like we had in our RMSprop. Okay. But it also make use of another for here history vector later also. Okay. But what will happen that when you are updating your gradients, what you are going to use for this U part, you are going to use UT minus 1. For this V part, you are going to use VT. So it's like you are going to maintaining two history vector. Okay. And your learning rate is defined by the square root of the one velocity vector divided by the square root of another velocity vector. Okay. But they goes by like one timestamp difference in both of them. Okay. And this division that we had of two history vectors, okay, is basically your learning rate here. Okay. And that's why we say that adaptive delta or ADA delta helps us avoid the case of setting initial learning rate. Okay. So that's the only thing that you can remember. The formula is a little bit complex and it's generally never asked in the exam. We usually can see the question from like conceptual based. So conceptual based, two things are there here, that it avoids setting us any initial learning rate. Second thing is it basically contains of two history vector and they follows the difference of one timestamp in them. Okay. Shall we move ahead? Okay.
Yes, sir.
Now, the final thing that we'll be covering in week 5 would be our Adam. Adam is the most powerful optimizer algorithm that is used uh, almost like in every start of our deep learning training. Okay, so it's the combination of your RMSprop and the momentum that you had. Okay, so we carries in momentum vector mt, that is beta 1 times mt plus 1 minus beta 1 times gradient of wt. Okay, so this is similar to what your classical momentum that you had, but in that momentum equation, if you are going to back and see, we did not have a that 1 minus beta term here, I think. Okay, but it adds beta and 1 minus beta in both. This should be mt minus 1. Okay, yeah, so beta 1 is here. Then we do something called as the bias correction. I will come to this part. What does it mean by bias correction? Okay. Then the another thing that we had is the velocity vector that we similarly had in the RMSprop. Okay, it's the exact same thing here. Okay, it's just that now we have this beta. Okay, in both the case for the momentum equation and for the RMSprop vector, we use different beta. That's why we have beta 1 and beta 2. Okay, so we are basically accounting both the case for the momentum case and the RMSprop case. And for both of these vector, we are doing something called as the bias correction. Okay, then your update for W is WT minus how we are doing with the how we are playing with the learning rate like in your RMSprop by dividing it by square root of VT. Okay. And in the case of momentum, we are basically using that directly here. Okay. So it's make use of both. Okay. So if you look at this equation carefully, this is basically just combining your momentum and the RMSprop all together. Okay. That's all it is doing here. Okay. And the important factor that we have to care about with Adam is the bias correction part. Okay, what I have written beta 1 and beta 2 as generally the value that we see or we set initially. Okay, but these are also like hyperparameters. Yeah, so main part, what is the bias correction here that we are doing here? Okay, so what will happen here that we are going to initialize our m naught, okay, this vector and v naught to be 0. So we are basically going to set our initial momentum vector and the velocity vector to be 0. Okay, and to account for the bias that we are going to create because of this, that we are setting our initial momentum and the sum of square gradient to be 0. This will create some bias when you are going to start off the training. Okay, if you are going to go back and see the lectures, Sarah has shown this with the graph that how this initial settings uh, creates the bias in the initial part of the training. Okay, and to overcome that bias, what we do is we divide our mt that we had or we got by 1 minus beta 1 power t. Okay, so it is beta 1 power t. Similarly, here it is beta 2 power t. Okay, now how does it help us? The bias is basically creating problem in the initial learning part. Okay, so as you move ahead and ahead in the time step, because beta 1 and beta 2 both are something that is between 0 and 1. Again, if you're going to put something to the like high power for the value that is there between 0 and 1, like if let's suppose beta 1 is 0.9 and you are at t equal to 10 iteration, and 0.9 power 10 will be very low value. Okay, so in that case what will happen that as you increase your iterations, okay, this term will become close to 0. Okay, so and then what you are going to left with is just simply vt. The vt hat is basically will just become vt. Okay, so that's why this is cleverly done that only in the initial learning part when it creates the bias for us. Okay, it will do this bias correction, and the later part when the training becomes stable, okay, it will automatically becomes equal to the its unbiased version. Okay, so that all is there in the Adam part. Any doubt here?
So we can proceed further.
Yeah. Okay, now let's start solving some questions from week 5. Which of the following optimizers uses adaptive learning rate? Can anyone give the answer? Which of the following
Oh,
optimizer?
first one, second one.
Yeah,
Hmm?
correct. What about momentum and the NAC? Does they use adaptive learning rate?
No, they don't use adaptive learning rate.
Yeah, correct. Okay. Only the algorithms that we are basically seeing in our week 5, these are the only one that use. Okay. Adam, RMSprop, Adagrad, Adadelta. Okay, then there are variants of Adam also that we have studied, but those generally are not asked. Yeah. So the second one that we just talked about, why is the bias correction needed in the Adam optimizer? Okay. So which option do you think will be the correct?
First one is probably correct, but let me see other options also.
Anyone else has any answer? Yeah. So as I said, that bias correction is needed because of we set the initial values of these MT and VT, okay, to be 0 to so to overcome that bias, okay, we do this bias correction, okay, and that's why the second option is correct here. Okay, we do not do the bias correction to prevent learning rate from being too high or too low, or to increase the effect of momentum, or to ensure that the learning rate remain constant. Okay, these are not the reason. The reason is that the initial values of the momentum vector and the RMSprop vector that we set, okay, that will create the
Oh,
bias in the initial part of the training. And to overcome that, we do the bias correction.
okay, understood, sir.
That's that's what technically it's like formally written here that to correct the underestimated moving averages of the first and second momentum. Here by that they mean this momentum vector and the RMSprop vector, the first and the second momentum. Okay. Yeah. Any doubt here till now?
No, sir.
So this is one I think numerical question. Yeah. Okay. So the weighted moving average is used to smooth the data by giving more importance to the recent values. Suppose we compute a weighted moving average for a sequence of the gradients by using this formula. Okay. Where VT is the weighted moving average, beta is zero point 0.9, gradient of WT is the gradient at timestamp t, and V minus 1 is 0. So if the gradients at these timestamp 0, 1, 2 are W naught is 5, W1 is 3, W2 is 4. Then we have to compute V2. Okay. Now this equation that is given here is basically similar to your RMSprop equation for the velocity vector. Only difference is that equation contains the squared, but this one does not. Okay. Except that everything is same. Okay. So now, as I explained earlier, here, okay, for any VT, it was 1 minus beta times this entire thing, which is basically whatever timestamp you are starting with, that timestamp will go in the power of beta multiplied with gradient at W naught. Then you are just going to decrease power one by one and start in the direction of W1, W2 at all. Okay. And beta 1 power WT minus 1. And for that timestamp on which you are, okay, it will not be multiplied by beta. It's basically, or technically it is beta power 0. So with this, if you add and tell me what will be the equation for V2 here. What will be the equation for V2?
Beta into V1 plus 1 minus beta into V2. I mean delta of W2.
You forgot W naught. Okay, so see, as I said, as here we have from 2, so I'll start with beta power 2 and it will multiply with W naught. Then beta power 1. Keep decreasing the power and keep moving ahead in the gradient part. W power gradient of W naught. And it's technically beta power 0 times gradient at W2. This whole has to be multiplied with 1 minus beta also. Okay. So now the remaining thing is basically you can just put in the values that you had. Beta was 0.9, so it will be just 0.1. And beta square is 0.81. Gradient to W naught is 5. And zero point 0.9 into gradient to W1 is 3. And beta power 0 is 1 plus W2, that is 4. Okay. So that's what you are going to do.
Why we are using this one?
Which one?
I mean, in this question,
Hmm.
uh, could you move a little bit up?
Yeah.
Yeah,
Yeah,
yeah.
they will get squared, but in the question we have not given the squared equation here. That's what I told in the initial part. Okay. In the RMSprop classical equation, we do the square, but here they are defining this weighted moving average by this, which does not have the square. That's why we are not doing it. Otherwise, if they mention, then you are going to do the square also here. So it will become 5 square, 3 square, 4
Oh,
square.
no.
Okay.
Okay, okay.
Yeah. Any more doubts? Yeah. The next question is basically based on the Adagrad update rule. So we have this loss function given to us. Okay, where W is the parameter for our model. And we are using Adagrad optimizer to minimize this loss. Okay, and the initial learning rate is set to 0.5. Okay, and the W we have the starting point is 2. We have given the update rule for the Adagrad. Okay, with V minus 1 0 and epsilon to be also 0. Okay, now this is what you have to calculate here. These 4 things like W1, V1, gradient of W1, and value of W after T2, so it should be just W2. Okay, so these are the 4 things that you have to calculate here. So it's again more or less like formula based thing. Okay, so I'll start off with 2 things here like W1 and V1. Okay, the remaining 2 I will leave you guys to do. Yeah, so with the formula and the things that is given to us, let's note it down. V minus 1 is 0, epsilon is also 0. Okay, W naught is 2. Our loss function is W cube plus 2W. Okay, if I have to take the gradient of this loss function with respect to W, what it will come out?
3W squared plus 2.
Plus 2. Okay, that will be the gradient. Okay, now you can just plug in the value of W to get the corresponding timestamp gradient. We have this, sorry, we have this initial learning rate also, that is 0.5. Okay, now we have noted down everything, so let's start doing the algorithm. So we'll start with this. We have to find V naught first. Okay, So for that it will be v minus 1 plus gradient at w naught square, because here we have the timestamp t. Here we have t minus 1. V minus 1 is given to us 0. Okay, so it will become v naught equal to 0 plus gradient at w naught square, that is simply gradient at w naught square. So we just have to find the gradient at w naught. So what will be the gradient at w naught using this?
Eight.
Mm, 5 bit,
And after that,
not 8.
uh,
It should be 2 square into 3 plus 2, right?
oh,
So
2
4,
square,
3,
that's a square.
right?
14,
So it's
14.
14. Okay. So if you plug the 14 here, you will get 196.
196, yeah.
Okay. That's your V naught value. Okay. To get W1, we have to do this. That's given here. Okay. So that is, if you follow the formula, it is W1 equal to W naught. Okay. Minus my learning rate, the initial learning rate, divided by the square root of Vt. Okay. That is my 196, the square root of that. Epsilon is 0, so it's just Vt only. So square root of 196. Okay. That will be 14 only, multiplied by gradient of Wt. So gradient of Wt was this. Current timestamp, that is 0. So it was the gradient is 14. So 14 only here. Okay. We will just cancel these two out. What you will get is W1 equal to W naught minus eta times just eta here. Okay. So it's 2 minus eta was 0.5. So 1.5. That's my W1. Is it clear?
Yes, sir, clear.
Okay. Now once you get W1, you can again calculate the gradients of W1. For V1, what you are going to do is it's V naught plus gradient at W1 square. Okay. V naught we have already known from here. It's 196. Okay. Now whatever the gradients comes at W1, okay, that you can easily find from this here. Just put the value of W1 here, that is 1.5. So you'll get gradient of W1. Okay. And you have to do the square of that. And with that, you will be able to get the value of V1. Okay. Now, if you're able to get V1, you can easily go to W2 using W2 equal to, yes, any doubt?
No, sir, no any doubt.
W2 equal to W1 minus eta by square root of V1. Okay, because epsilon is 0. Okay, multiplied by gradient at W1. Okay, so the remaining things are just mathematical calculations. So try it out by yourself. Okay, you can get the answer for these in your past QP. Okay, so you can check it from there. Is the method clear? Okay. So again, 2, 3 more theoretical questions. Which of the following optimization algorithms adapts the learning rate based on the current and the history of the gradient? Okay. So which among these 5 is the correct one? Okay, B. Yes, B is correct. Any other than that B? E. Yeah, that is also correct. Anything other than B and E? What about Adam? Adam also do this, right? Because Adam contains your RMSprop. Okay. So if RMSprop does this, then Adam also does this. So that's why this will also be correct. Maestro, of course, it does not have the feature of our adaptive learning rate. Gradient descent with exponentially decaying learning rate is something that we do for scheduling the learning rate, but it does not make into the count of the history of the gradients to do that. Okay, let's make use of the formula for the exponential decaying part. Next
Mm,
question.
6
Yeah.
would be Adam. Adam. No, no, I'm talking about 6. It would be Adam. Option B.
Uh, yes, it's Adam only. Okay. Adam make use of both, as I said, RMSprop and momentum. Last one. What is the
Option
key
B.
reason for
Option B.
development? Correct. To adapt the learning rate for each parameter dynamically. Okay. B. 5 we are done. Any doubt?
No, sir, no any doubt.
Okay, so week 6, the first part of week 6, kind of like we can divide it in two parts. First part mainly covers something from your MLT also, and the stats 2 part, that is the bias variance trade-off. Okay, the next important thing after that is your regularization methods. Okay, so these two are the main important topics from your week 6, bias variance trade-off and the regularization methods. Okay, so now this is the one example that Prof has started with, that if you have a simple model, something like W0 plus W1x, and if you have a little bit more complex model, something like W25 power times x power 25 plus W24 times x power 24, like that. Okay, then which one of the model here is more likely to overfit? I have one simple model like this, and I have one very complex model like this. Suppose you are training this on a sinusoidal training curve. Then among these two models, which one is more likely to overfit?
Mm, a complex model will overfit.
Yeah, correct. Okay. So the case of overfitting and the underfitting, that things are same like in our MLT. If you have a complex model, then it's likely to overfit. Overfit is the problem that you are able to uh, good get good score in your training data set, but on your validation or on your unseen data set, you are getting a very bad score. Okay, that's simple definition for overfit. For underfitting, it's the kind of opposite case, that, but not exactly the opposite, that underfitting models are basically so simple models that in both the training and the test dataset, you are getting bad score. Okay. So what you basically generally try to find is a sweet spot between the complexity and the simplicity of your model, because it cannot be too complex, otherwise it will overfit. Perform will Performance will be good on training but not on test, or it cannot be too simple, otherwise performance will be bad on both training and the test. Okay. Now these things are basically controlled by our bias and variance. Okay. So starting off with the bias. Okay. So what is bias? It's basically, in terms of our model definition, it's like on an average how your model performs. Okay. So you have this f hat of x. Okay. F hat of x here is your model. So you are going to, let's suppose, train f1 of x, f hat 2 of x. Okay. What does this f hat 1, f hat 2? These are some, let's suppose, different models that you are trying. Okay. So one model can be like something y equal to x, one is like y equal to w1 x1, something like that. Okay, so different models that you are trying, that are being represented here by f1 at x and f2 at x. Okay, then you are taking the average of that. Exponential here is basically means average. Okay, so exponential of sorry, not exponential, expectation of f hat of x. Okay, it's basically the average of the uh, prediction that you are getting from each of these different models, and you are going to subtract it from the true prediction, the true value for that data point. Okay, so this is the ground truth value. Okay, so this is your simply y. Okay, now this is basically you are by training different model, you are going to get different y hat 1, y hat 2, y hat 3. You are going to take the average of these, whatever you are going to get, y hat mean. Okay, that difference of y hat mean and y is your bias. Statistically, this is what it is by with formula. Okay, so is it clear?
Yes, sir, clear.
Now the variance on the other hand is this. It's the expectation of f hat of x minus expectation of f hat of x, the whole square. Okay, so expectation of f hat of x is simply the same quantity that we had here. Okay, average of all the prediction that you are getting. And how does this average prediction is getting difference from your prediction from each model? Okay, so again, let's suppose you had this uh, y hat 1, y hat 2, y hat 3. You're going to get a y hat mean, that is the average prediction. Then y hat 1 minus y hat mean the square. Okay, because you have the square term here. And similarly, y hat 2 minus y hat mean square. Y hat 3 minus y hat mean square. Okay, you are going to add them up. You are going to divide it by the 3 because you are taking the average here. So average of these three quantity, because we have you have here outer expectation also on this term. Okay, so that's your variance. The net quantity is same as expectation on the predictions, and you are going to subtract it from each prediction value and do the average thing here again. Okay, so it's the variance. Okay, roughly what we call as our variance is basically how much different your each prediction is from the average prediction that you are making. Okay, more simpler words is basically how much fluctuation your model is making with respect to each new data point. Okay, so is the variance clear? Okay, very good. The final point is, if you have the simple model, it will have high bias but low variance. Okay, reason for high bias is the model is simple. Okay, so the average prediction will be very close to each other. There will be not very much fluctuation. Okay, so this difference will be very high. Okay, variance would be low because the difference will not be very much from each of these predictions. Complex model will have low bias, high variance because each of them are complex models, so their differences in the prediction will be different. Okay. So that's all is in the bias variance trade-offs. Any doubt?
No, sir.
Now the second part for week 6 is your uh, regularization methods. So that's what we are going to discuss now. Okay, so let me first note down what are the methods that you have. Okay, L1, L2 regularization you have. It's simply the same thing that you did in the MLT, the L1, L2 regularization. You have early stopping. Okay, there's some part of this is you studied in your MLP at least. Data set augmentation. This is also something if someone who did the MLP course last term, then we have introduced a new syllabus for MLP, the image classification. In that we have covered this. But don't worry, we will be covering this here also. Fourth one is the parameter sharing. The fifth one is the injecting noise at input flash output. And sixth one is ensemble method. Okay, so the bagging, boosting, random forest that you studied. The seventh one is the dropout. Okay, so these are the regularization methods that you have to remember or that are there in our course. Okay, I'll start early with few parts which I believe you already know. Okay, just like the L1, L2 part. Okay, it's the same thing that we did in the MLT. You have your loss function. Okay, in that what you are going to do, if it is a L1 regularization, then what will come? What you do in the case of L1 regularization, you add the absolute values of your parameters, right? So absolute summation of your parameter values. Okay. If it is the L2 regularization, then it's the squared summation. Okay. Typically the L2 norm or the L1 norm. Okay. So that's what you do in the case of L1 or L2 regularization. Okay. This basically helps us uh, our like control the magnitude of our parameters so that it does not blow up. Okay. And of course you just does not directly add them, you add them by some penalty lambda. Okay, so the original loss function plus if you are doing the L1 regularization, it's just lambda 1 times summation of the wi value. So w here can be like your vector, so 1 2 3, and it will be just lambda times 1 plus 2 plus 3. In the case of this, it is 1 square plus 2 square plus 3 square. Okay, so L1 norm or L2 norm. Okay, clear? Moving on to the second part, that is the early stopping. So what early stopping says that mm, let's suppose this is your loss curve. Okay, so I'm plotting your loss curve by each iteration. Okay, so early stopping simply says that if by some window, okay, you are going to set this window by yourself, so it's kind of like a hyperparameter. If within some window your validation loss is not improving by some tolerance amount, okay, then you are going to stop the training. Okay, so you can say like this is something that you got at iteration 5 and this is something that you got at iteration 10. So your window is like 5 iterations. So this is called as the patience generally. Okay, patience of 5 iteration. Okay, so within these 5 iteration, your validation score, okay, that you calculate on your validation data set, if it does not improve by some tolerance amount, okay, again, tolerance is something that you are going to set, okay, like tolerance can be like 0.001. If it is not improving by this much amount at least, okay, then you are going to stop the training. Okay, so this is called as the early stopping. Okay, clear? Great. Next is the data set augmentation. Okay, so it's mostly used for the images on the audio. Okay, so suppose you have an image. Okay, now with the image, what you can do is you can basically rotate the image, you can crop the image, you can scale the image by some factor, you can uh, blur the image. Okay, add some effect like that. Okay, and by doing these multiple operations, you can create new images. Okay. Now, condition that the label for the image does not change, you can do all of these operations to create a new data set for your model. Okay. And in this way, you are going to get free data, label data basically. Okay. So it will also enhance your training score. Okay. Now, as I said, the condition here, because let's suppose you are training on your MNIST dataset. The MNIST dataset contains the handwritten digit. Then in that case, if you are going to vertically flip the image, then the 6 image can become 9. Okay. So you have to do the data augmentation in such a way that the label of the image does not change. Okay. So condition that it does not change, then you can either rotate it by some angle like 30°, 40°. Okay. Vertically flip it, horizontal flip it. Okay. Crop the image by some factor, scale the image by some factor. Okay. All sort of things you can do with the images here. Okay. To create more data set for you. Clear? Next in line we have parameter sharing. So parameter sharing is something that I will cover at the time of CNN. Okay. So basically in one line, parameter sharing basically helps us reducing the number of parameters in the model. So if the parameter will be less, then your model will be less complex. So again, it's kind of a regularization. Okay. But it will be more clear in the case of week 8 because in that we apply it in CNN parameter sharing. Okay. Next one, injecting noise at input or output. Okay. So what you can do is for the input case, if we see, if you have your this image again, okay, then you can change or add some noise in the input. Like you can, for each pixel values that you are going to have, okay, you can add some like Gaussian noise to each of these pixel values. Again, the condition is same that as long as the label does not change. Uh, okay, so you can add these noise. Okay, this is to again so that your model is able to become more robust. Okay, for the output case, what we do is now, till now, if you have seen or remember that the y vector that you had for the multi-class classification problem, we generally convert it into a one-hot encoded vector. Okay, like this. Just give me 1 minute. Yeah, 1 minute, please. Yeah, so let's continue. So for the injecting noise at the output, what I was saying that we generally had this one-hot encoded vector, right? For the multi-class classification. Okay, so 100 means the label is the first class. 010 is the label is the second class, like that. Okay. Now this is kind of forcing that the class would be only one, not other. Okay, so we are fixing it. Okay, it's the intuition is similar to what we have the intuition from switching from perceptron to the logistic. In the perceptron, we have this steep model. Okay, where something is either 0 or something is 1, nothing in between. Okay, so the intuition is here also same, that we are going to inject the noise here to the output, and that is basically done as in some way that you are going to subtract some epsilon quantity from this. So 1 minus epsilon, okay, and that epsilon quantity, whatever you are subtracting, you are going to add that quantity to the remaining one, equally distributed. So as here there were two, so you are going to equally distribute this as in these two. Okay, now again what will happen, that if you are going to sum them up, okay, you are going to get one. So this is kind of like we have like a probability distribution thing. Okay, so if you would have like some vector of 5, okay, then the injecting noise at output will look like 1 minus eta, or for 1 minus epsilon, then this epsilon will be divided into these four parts. So epsilon by 4, epsilon by 4, epsilon by 4, epsilon by 4. Okay, so this is the injecting noise at the output. Okay, now what this will make change, previously our cross entropy loss, okay, we used to define it as negative logarithm of y hat, okay, where y hat was the probability for my true class. Now the reason why we were able to define our cross entropy loss like this, because previously we had our labels like this, okay, where either we had the 0 or the 1, and 1 was only at one place where we had the true class. Okay, but here because we are going with this manner, okay, we have to switch it back to the original cross entropy formula that we had. Okay, and that was negative y ln of y hat. Okay, so for this vector that I created here, if I'm going to calculate the cross entropy loss, then it would be uh, negative, if I take common, 1 minus epsilon ln of whatever the probability I'm going to get. So let's name it as y1, y2, y3, y4, y5, then y1 hat plus epsilon ln of y2 hat plus epsilon by 4, epsilon by 4, ln of y3 hat, and so on. We are going to sum them up, multiplied with negative sign also. That will be your cross entropy formula. Okay, so this thing will change when you do the injection of noise at the output. Okay, is it clear? Okay. Yeah, so two things remaining: ensemble methods and dropout. So ensemble methods is same what we had studied in MLT, your bagging or boosting methods. Okay, so what used to happen in the bagging is basically we are going to combine multiple models in place of one models and average their prediction. Okay, now this fact that this will work and reduce the variance of the model basically comes from our stats part for weak of large number. Okay, so assume that you have some independent and identically distributed variables z1, z2, z3, z4, like that. Okay, now each of these has uh, let's suppose variance of sigma square. Okay, now because these are identically distributed uh, variables, okay, their variable of z hat, that is 1 by n, if I have n variables, z1 plus z2 plus z3, zn, this will be my mean z variable here. And if I'm going to find the variance of this, okay, this will be 1 by n times sigma square 1, because each of these has the variable of sigma square, plus sigma square plus sigma square plus sigma square. Okay, now because they are IID, okay, and that is the reason why we can write the variance of a plus b equal to variance of a plus variance of b. Okay, this can only be written when you have the independent variables. Okay, and that is the reason we can split this part into 1 by n times sigma square. Okay. Now you are finding the variable here, variance here, and variance is one more property, that variance of alpha times a is basically alpha square times variance of a. Okay. So using this property, it will be basically n square sigma square. Okay. Sorry, not sigma, n square will not come here, n will become here, because we are scaling by this part, not this. This n is coming because we have n times variance. Okay. So 1 by n square times n times sigma square. This will cancel the squared part, and you're left with sigma square by n. Okay. Now this whole calculation is just to show that if you average, if you take the average of IID variables, okay, the variance will get reduced. Okay. This whole thing was just to show that. That's what we're trying to implement in the bagging case, that we create multiple models. Okay. For now, think of the example for our decision trees, that from my existing data set, I will randomly sample, create some bags, and on each of these bags, I'm going to train my model. Okay. So I will be having multiple models. And for the prediction, what I'm going to do, I'm just going to take the average of the prediction. Okay. Now, the fact that this will happen, that is, the variance is going to get reduced, will only applies when the first condition hold, that we initially assume that these are independent. Okay. Now, it can or it cannot happen that the models that you are going to train may be independent or may not be independent. In the bagging, it is not guaranteed that it will be independent. Okay. So from the bagging, we switch to the random forest part, that basically tries to ensure that the models that you are going to train are uncorrelated to each other. How it is done is basically, while training our decision tree, for each split in the node, you are going to take a subset of your data features. Okay. So for each node in the decision tree that you are training, okay, for each splitting, you are going to take a random subset of the feature every time for each model, for each node in that model tree. You are going to take a random subset every time. And that is the reason why each model will be different to each other. Thus, you are going to get a IID set or independent set of models. Okay. And then this will clearly get applied, that the variance will get reduced. So, of course, if variance is reducing, then the performance will be increasing. Okay. So that's for the random forest part. Okay. So those are your ensemble methods. Now, final regularization method that is remaining is your dropout. Okay. Now, one question that comes from dropout before applying the dropout is the thing that we were doing in the case of ensemble methods. Okay. That we were training multiple traditional ML models together. Okay. Question arises, why can't we do it for our deep learning models also? That we can even train multiple deep learning models together and then combine their outputs. Okay. The obvious reason for that is training one deep learning model is already computationally expensive task. So training multiples together simultaneously will be more computationally heavy. Okay. So that's of course one of the reasons why we cannot do this. Okay. Or replicate the same thing that we were doing in the case of traditional ML models. Okay. Now dropout is kind of like an roundabout way for doing the same thing that we were doing in the case of ensemble method. But it's kind of like a flexible way of doing the ensemble method for deep learning models in a very clever way. How it does is, suppose you have your A and N here. Okay. Of course, each neuron here is connected to the every neuron here. Okay. What dropout does is, at the time of training, okay, except the input and the output layer, okay, in all these hidden layers that you had, at the time of training, each hidden layer, each neuron here will have the probability P that it won't be active. Okay. So for example, let's suppose in the first iteration, this neuron here and let's suppose this and this here, these were dropped or they become inactive. Okay. So then you will get like a kind of shallow version of the above neural network. So shallow version means you will get just 3 from here, 3 from here, and 3 from there. Okay. Because 2 neuron from this layer, 2 neuron from this layer is dropped out. Okay. It's not necessary to be the same. It can be like 3 can also be dropped out. Okay. It's just that each neuron in the layer will have the same probability P that it will stay. Then 1 minus P will be the basically probability that it won't stay. Okay. So this is what dropout is going to do. In each iteration of forward and backward pass, okay, okay, each neuron will have the probability that it will drop or it will become inactive. Okay. Then you will get this kind of a shallow network. And then you are going to do the forward pass on this and do the backward pass again on this shallow network only. Okay. So only the neurons that are there in this forward iteration, only the weights corresponding to those neurons will get updated in the backward pass. Because these neurons became inactive in this case, that is the reason that in that iteration, particular iteration, their weights will not get updated. Okay. But it can happen that in the next iteration of my forward backward pass, these neurons that were initially dropped, they might stay, but other might become inactive. Okay. So it's totally probabilistic way. Okay. In every iteration, okay, there will be same probability P for every neuron to stay or to drop. Okay. Now the intuition behind this for using is, uh, let's suppose you are doing the image classification, then some of the neurons might be like focusing or might be dominating in predicting the output. And you do not want that your entire output depends upon a subset of very few subset of neurons. Okay. So by dropping some of the neurons randomly in each iteration, you are forcing other neurons to learn more good representation. Okay. Because now after dropping them, other neurons will have to carry the weight of doing a good outcome. Okay. So that's the intuition behind dropout. Now this dropping part of neurons is technically or done at only training time only. At the inference time, we do not drop any neurons. We will take our entire original structure. Okay. And what we are going to do is the output, sorry, the out the output of each neuron, okay, will be scaled by its probability. Okay. So the reasoning behind this is because my neuron at the training time was only active by probability P. Okay. That's why at the inference time also it should only have the weightage of P times P. Okay. So output of every neuron here will be scaled by P. P here is the probability that the neuron will stay. Okay. So if the neuron original output was something like let's say 5 and my probability here was 0.2. Okay. Then the output of the neuron will be 5 times input 0.2 1. Okay. That will be the output that will go to next layer. This will happen for every neuron here. Okay. So this is the dropout. Any doubt here? Okay. Let's moving on to the questions. The first question says that consider the 4 training experiment, each involving a neural network trained on the different data set for 50 epochs. The loss curve for these models are shown below. Okay. The model obtained at the end of 50 epochs is retained in each of the 4 cases. The solid curve is the training loss and the dashed curve is the validation loss. Okay, so we have these four statements. Learning rate is too high, low bias, high variance, low bias, low variance, high bias, low variance. Then we have to choose the most appropriate pairing of the models with the statement. Okay, so we have these loss curves for the training and the validation. And with that, we have given these four statements. So we have to map each of these model M1, M2, M3, M4 with ABCD.
M1 would be C because it has low bias and low variance also.
Yeah. Can you give the reasoning for that?
From this graph, as we can see that both graphs are, I mean, no, there are no huge difference between them.
Very good.
That's
A low bias and low variance model will be such model in which your loss for training and the validation are there is not very much difference. Okay. So after the training, if you could see, the training loss and the validation loss are close to each other. So this is kind of like a low bias and low variance model. That's why M1 will be mapped to C. Okay. Now what about M2? Where is this is the M2? What should be the statement for which we should map M2? Okay, then tell me about for M3 first. M3 might be easy.
M3 should be, I think, low bias and high variance,
Hmm, correct.
and
So low,
M2 should be like it has high bias but low variance. So M2 can be,
okay,
M2.
M3 is correct. Low bias, high variance. I hope the reasoning is also clear to everyone because after a certain number of times, your validation loss is increasing but training is decreasing. Clear case of overfitting happens in the case of low bias, high variance.
hmm M3 is okay.
Okay. M2 and M4 are remaining. And we have the statements that learning rate is too high and high bias and low variance.
Yeah,
What
so
happens in the case of high bias and low variance?
in case of high bias, I think none of the sorry, the model won't fit either the training data or the testing data.
Okay,
So
very
that
good.
should be M2.
M2, okay. Uh, yeah, then what about M4?
But yeah, M4 again we can see that it plateaus off at some Y value, but learning rate used is too high.
Yeah.
I'm not
First of all,
sure.
somebody asked that she is not getting the graph. So the graph is basically the loss versus epoch graph. Okay. So the x-axis is your epochs, number of iteration for which you are training. Y-axis is your loss. So what you are doing, you are training four different models. M1, M2, M3, M4 are your four different models. Okay. For each of these model during training, you are plotting your training curve and validation curve. Validation curve is this dead dash curve. Okay. Training is this solid curve. So for each of these four models, you are training your loss curves for training and the validation. Now using this curves only, you have to figure it out which of the following statements will be correct fit for these models. M1 will fit to C option or the C statement because the training and the validation loss after the end of training is close to each other. That happens in the case of low bias, low variance. M3 will be fit to this part because at the end of training, your training loss is very low, while validation loss is very high. Clear case of overfitting. So that's why low bias, high variance. Remaining for these two, M2 and M4. Okay. Now start off with what happened if you set the learning rate to be very high.
If the learning rate is too high, then the gradient descent algorithm will jump too much and it might go into another high loss area.
Yeah, it can overshoot your minimum.
Yeah,
Now look at the graph of M2, what's happening? You have the loss initially
yeah,
very low, but you then overshoot quickly to some high value loss.
okay.
Okay. This is what happens generally when you have the high learning rate. Okay. So that's why it will be mapped with A option. Okay. Now in the case of M4, okay, what is happening at the end of training? Your validation loss and the training loss both are high. Okay. Now low will be when it will be like here. Okay. But because both are like quite at high position, okay. So that is the case when you have the high bias low variance in underfitting case. Okay.
So if you're talking about high bias, then that just means that the model isn't able to perform well either on both the training
Training
or
and the
testing data.
validation. Yeah.
Okay. And variance is just the difference in performance between the training data and the validation data.
That's not the exact definition of the
Okay.
variance. The variance is like your model is not performing well on the unseen data set.
Yeah, unseen. Okay. Like it performs really well on the training data, but not
Mm.
as well in the testing data.
Yeah, correct. Okay, so I think the first option matches with that. Okay, M1 with C, M2 with A, yeah, M3 with B, and M4 with D. Yeah. Any doubt here?
No.
Okay, starting off with the second question. An encoder in autoencoder is a feed-forward neural network in which the input and the output layer have the same number of neurons. Okay, so if you have like 5 neurons here, okay, in the input, then 5 neurons will be there in the output layer also. There is one hidden layer in between, okay, and the number of neurons in the hidden layer is 30% of the neurons present in the input layer. So it will have like 30% of the number of neurons that is there in the either the input or output layer. Now, call the two weight matrix W1 and W2. Ignore the bias everywhere. We now consider two instances of the architecture. Network 1, where W1 and W2 are not tied, meaning they are two different weight matrices with no parameter being shared. Okay, that basically means both of them are different metrics. There's no sharing of parameters. Second case, W1 and W2 are tied, meaning W2 is W1 transpose. The parameters are being shared. Okay, so it's just that you are using this W1 here. Okay, the same W1 is kind of used here, but in the transposed manner because computation is going to flip here. Okay. Now both networks are trained on this data set and their parameters are saved on hard disk with efficient storing. That's all. The number of parameters that needs to be stored in the network 1 and 2 are N1 and N2, and find the ratio of N1 and N2. So tell me, what will be the answer for this?
Um, so what network 2 is basically doing is that, let's say that it takes in 10 inputs.
Hmm.
So it's compressing those 10 inputs down to 3 inputs and then decompressing them back and giving them out
Hmm.
in the output layer.
Yeah, correct. And for
So
that, it is only using one matrix.
yeah, so 1 by 2 should be the answer, I think.
It will be 2, not 1 by 2.
Oh yeah, sorry, N1, yeah, 2
N1
by
by
1,
N.
yeah, 2 by 1, sorry.
Because W1 and W2 in the network 1 are two different matrices. Okay. The size will be the same here because the size for W1 would be the number of neurons in the input layer times the number of neurons in the hidden layer. For the W2, number of neurons in the hidden layer times the number of neurons in the output layer. So as the number of neurons in input and output layer are same, so the size of W1 and W2 in both the network structure will be same. It's just that because W network 2 uses the same matrix, here the number of parameters would be half technically than the network 1. So when you are going to take the ratio, you will get 2 here.
One question regarding the architecture. So,
Hmm.
like I said, that network 2 is doing the compression and decompression thing.
Yeah,
So, is network 1 also doing that same thing? Because if we run that through back propagation, we
yeah,
might be
it's
able to
doing
achieve.
the same thing but with different
Okay.
parameters. The
Okay.
reason why half in the second parameters, is because it is given in the question itself that
Yeah.
W2 is W1 transpose. So the same matrix you are using here, the same matrix will be used here, okay, with the transposed version of it. So this is what it is basically called as the shared parameters. Any doubt here? So answer
No,
will
sir.
be 2. Now third one comes from the case that I studied, we studied just now, injecting noise at the output. Okay, so we have a multi-class classification problem with 5 class for a data point x comma y with true label vector is this. We decide to inject noise at the output so that the noisy true label y noise is this. Okay, so what we basically do, we have basically subtracted 0.1 from this one. Okay, so the epsilon here is 0.1 and we divided that 0.1 equally on the remaining classes. So this is my y noise. Then a network trained for this problem outputs the following probability distribution for this y hat, and just we have to find is cross entropy loss. I have already written down that equation here while we were doing that. Okay. The same kind of equation will be used here. Okay, as our y noise is just 0.9, 0.025, 0.025, 0.025, 0.025. Okay, and y hat, the predicted probabilities is 0.6, 0.1, 0.1, 0.1, 0.1. So cross entropy loss is negative 0.9, ln of 0.6. Okay, these are the probabilities. So probability will go in the logarithm part. And negative 0.025 times ln of 0.1. Okay, then negative 0.025 ln of 0.1. Okay, negative 0.025 ln of 0.1, negative 0.025 ln of 0.1. Okay, rest is just the calculation that you can simplify. Okay, so any doubt in this question? Okay. Yeah, this is
So just one thing about that.
yeah.
What would the answer be, like 0.069 or something?
I'm not sure of the answer. I think this was the question from last year paper.
Okay, okay.
Last year quiz paper, you can look at that. Yeah. The next question is from L2 regularization. So we have an ML model for which the unregularized loss on the dataset D as a function of parameters vector W, W1, W2 is this. So it's the unregularized loss. We have not added the regularization. This is denoted as LD. And the L2 regularization term LR is half lambda times norm of W square. Okay, where lambda is greater than 0. And this is the regularization rate. The L2 regularized loss or the total loss is LD, this unregularized part, plus LR, the regularized part. And then we are defining two W star. W star D is basically the argmin of LD, the unregularized version. And W star is the argmin of loss, that is the regularized version loss. Okay. And the argmin returns the value of W at which the function attains its minimum. Okay. So one difference here. Argmin is the value of the W. Okay. And min is basically the value of the function. Okay. So argmin is the value of the W at which function attains its minimum, not the value of the function. The sub questions are independent of each other. Okay, first very good question is just finding the W star D. Okay, so argmin of LD. LD is this. So what it will be? You just have to find the point on which this function attains its minimum, the LD.
1 comma 1.
Yeah, correct. Okay. So it's simple optimization part. Okay, you can just take the gradient of this function with respect to w1 and w2. You are going to get 2w1 and 2w2 here minus 2. Okay, set it to 0, then you are going to get w1 and w2 to be 1 and 1. Other way you can see is this is if you simplify this function. So it's kind of like w1 square minus 2w1 plus 2 plus w2 square minus 2w2 plus 2. So this part is w1 minus 1 square. Oh, sorry, no, plus 1 here. The second part is w2 minus 1 square. Okay, so it's the sum of two squared values. So it will attain its minimum when both of them are 0. That happens when w1 and w2 are 0. Okay, two ways to solve this. Okay, so the point on which we are going to get the minimum is 1 comma 1. Any doubt here?
Could you explain it?
Okay. See, what they were asking in the first part is find w star d. W star d is the argmin of LD. LD is this function. Okay, so we have to find the point on which this function attains its minimum value. Okay, and to check that, what we do is we take the gradient of the function, set it to 0, whatever value you are
Hmm.
going to get, that is the case. Okay. We found the gradient of this function with respect to w1 and w2. So this is the function. If you're going to take the gradient, it will be 2w1 minus 2 and 2w2 minus 2, right? Okay.
Yeah, okay, okay.
Now if you set it to 0, you are going to get w1 and w2 be 1 and 1.
Okay. Okay, sir, understood.
The second question, if w star is zero point 0.5 comma zero point 0.5, then find lambda. What is w star? W star is the argmin of my loss function. L is LD plus LR. Okay, so LD was this, LR was this. The addition of these two is my L. And for that L, we have to find the argmin. Again, the procedure would be the same. Find the gradient of this combined function, set it to 0. You are going to get the equation for your lambda. In the question, it is already given that it is equal to 0.5. Set it equal to 0.5, you are going to get your answer. Try it and tell me what will be the value of lambda.
Can you show the equation again?
Mhm.
Um,
Yeah.
Sorry, sir, just one more clarification. We are supposed to take W as zero point 0.5, comma zero point 0.5, right?
Not W at zero point 0.5. See what in the question it is given that W star is zero point 0.5
Okay,
comma zero
okay.
point 0.5. Okay.
And we use 1,
Oh,
comma 1 from the previous question.
that was for W star D for
Yeah.
this unregularized part. Okay, W star is for the regularized part. Okay. So
Okay.
after adding the regularization, if you take the gradient and equate it to 0, okay, the value that you are going to get after solving that equation is what they are saying, that it is 0.5 comma 0.5. But
Okay.
because we have this lambda term also, so when you are going to take the gradient of the regularized loss and set it to 0, okay, you are going to get lambda term in your equations. Okay, so you have to equate it to 0.5 also later on, and in that you will be able to get it. Okay.
It's coming as 0.5.
I think it should be correct. Let me see. Yeah, others have it right.
What I did was that I just took a gradient of the equation L equals to LD plus LR. So
Hmm.
you'd get the gradient of LD, and the gradient of LR would be just sorry, lambda W, right?
Yeah.
And I'm taking W as 1 comma 1 from the previous one.
No, it
Okay.
not be like that. Yeah. Uh, okay, let me solve. Okay, my loss function is the unregularized part plus the regularized part. So it would be W1 square plus W2 square plus plus or minus 2W1 minus 2W2 plus 2, then the regularized part, that is this. Okay. Now this part I can write it as half W1 square plus lambda by 2 W2 square. Okay. We can write it right like this because that's what the norm square of W represent, right? Okay. Now you can simply take the gradient of this loss function. So you're going to get 2W1 minus 2 plus lambda, right? Lambda W1. 2W2 minus 2 plus lambda W2. You're going to set this to 0, 0. Okay.
Oh,
So 2W1 plus lambda W1 minus 2 is equal to 0. Basically, the same equation carries forward for the W2 also. So you're going to get the same answer. So you can take the W common, 2 plus lambda equal to 2. W1 is 2 by 2 plus lambda. Similarly, you will get W2 also 2 by 2 plus lambda. Now, this is given to you as 0.5 because this is the W star, right, that you got. And that's what they are telling you, that if W star is this, then find lambda. So if W star is this, and if you're going to find the lambda, 2 by 2 plus lambda is equal to 0.5, 2 equal to 1 plus zero point 0.5 lambda. Okay. So lambda is 2.
yeah.
Okay.
I don't
So
know
any
why I didn't equate the thing to 0, comma 0.
uh, no problem. It's okay.
Yeah.
Yeah. Everyone got this question? Okay. The final question for this part, I think, that is there any value of lambda greater than 0 for which this case happen, that the norm of W star is greater than norm of WD. WD was unregularized one, W star is the regularized one. So is there any case where the norm of W star becomes greater than the norm of WD for lambda greater than 0? And if it has happened, then is it only one value? Are there infinitely many value? Are there finitely many value? Or there is no such value?
So if we take lambda to be something extremely close to zero, so because
Mhm.
W1 is given as 2 upon 2 plus lambda,
Very
then
good.
W1 would end up becoming 1 itself.
Very good.
And because it's 1, so that's literally like the least value, the best value of W1.
Mhm.
So, I mean, it would become 1, right? And
Yeah. The W star D what you got is 1 comma 1. See,
1,
when you are going to get W1 1, when lambda would be 0.
yeah,
For any value greater than 0, you are going to get something greater than 1.
yeah.
It will be 1.0001. Something would be greater than 1.
No, something less than 1, right?
No, no, no. Oh, yeah, yeah, sorry, my bad. Yeah, less than 1. Okay.
So it would never happen.
It will never have. Correct. Okay. So answer would be D. Because while solving our this regularized form, we got that W1 is 2 by 2 plus lambda. If lambda would be strictly greater than 0, then 2 by 2 plus lambda has to be less than 1. If it becomes less than 1, then because my W star was 1, so it cannot be the case that W star norm would be greater than W star D norm. Okay. So for any case, it won't happen. Okay. Yeah. Any doubt in this question? Okay. Now, few more uh, questions. What is the primary purpose of using algebraic regularization?
It should be to prevent overfitting by adding the sum of squared values of the weights to the
Yes.
loss function. Like that's the
Right.
literal definition. So,
Yeah. What is the soft target used when injecting noise at the output?
uh, a label that is 0, 1 with no target value that is continuous. What does a soft target mean?
See, what they're asking is what happens in the case of injecting noise at the output. So previously, when we have used to have is
Yeah.
this hard value, either 0 or 1. In the case of injecting noise at output, what we do, we make it like a continuous or a probabilistic way. We subtract some amount of some epsilon from the 1 and divide it equally in the remaining part.
Okay, so the new one that has injected noise is called the soft target.
Yeah.
Okay.
So this is the soft target. Okay.
Yeah.
Because it is not hard. Hard here means is either it will be 0 or 1. We make it soft that each one here has some probability or continuous values. Okay. So that's what your soft target is. So correct answer for this would be the B.
Yeah.
Okay. That we inject uh, while injecting noise at the output, its target value becomes continuous or the probabilistic rather than the discrete one, 1 or 0. Okay. Moving on to the next one, x upon the variance. Okay. And I think if you go more into the previous term, then you might find a similar question for the bias also. So consider a neural network architecture for the regression task. A distinct subset of the training dataset are used to train three distinct models, A, B, and C. So we have three models, A, B, and C. Note that these models have the same architecture with different parameter values. So consider a test dataset of the size 4 with Y true labels are 1, 3, 6, 8. So Y true is 1, 3, 6, and 8. Model A prediction. So model A 1, 4, 7, and 8. Or B 3, 5, 6, and 9. For model C, 2, 3, 5, and 7. Okay. Calculate the variance of these models averaged over all the data points in the test data set. Yeah. So try
So we
calculating.
calculate the variance of each model and then average that.
See how the variance is getting calculated. It's expectation of f hat of x
Yeah, why minus?
minus expectation of f hat of x, the square. The first part, or this part here, the expectation of f hat of x, it's the average of the prediction that you are getting through different models. So we have
Yeah.
three models, A, B, and C. Okay, this is I'm doing for one data point. So let's suppose we take this data point. The prediction for model is 1, for 2 is 3, for 3 is 2. So the average prediction here is 1 plus 3 plus 2 divided by 3. 3 to 5 and 6 by 3, 2. So I will call it as expectation of f hat of x. Okay. So I got this as 2, the average prediction. First, you have to find this
Okay, so we take the average for each class rather than each models.
for each data point.
Yeah, okay.
Okay. You take the average, then you have to subtract it from the each model prediction. So 1 minus 2 the square plus 3 minus 2 square plus 2 minus 2 square. Take the average again because again you have this outer expectation. And because it is also saying averaged over all the data points. So this I was doing for one data point. Do it for the all the four data point. Take the average. That's your final answer. Okay. So let's first calculate the expectation of f hat of x. So 5.9 plus 312 by 3, 4. 13, 5, 18, 6. And 17, 24, 8. Okay. So this is the average prediction. Next thing I have to find is for each of this f hat of x minus
Sorry
6.
to interrupt, sir. Can you
Yeah.
please go how the averages are, sorry, the expected values are being calculated again? Because like,
For
uh,
this average,
yeah, yeah,
it is 1 plus 3 plus 2 divided by 3.
oh yeah, divided by two. Okay, so yeah,
4 plus 5 plus 3 divided by 3.
yeah.
Now, for each of these models, you are going to take its prediction, subtract it from the average prediction. Okay. So I have to take here the data point. Data point 1, 2, 3, and 4. So for the first data point, my model A prediction is 1, average prediction is 2. 1 minus 2 square. Model B prediction is 3, average prediction is same 2. Model C prediction is 2, average prediction is 2. Take the average, you're going to get 1 plus 1, 2 by 3. Okay. Same thing you are going to do for the second data point. For second data point, my model A prediction is 4, my average prediction is 4.
It would again be 2 by 3, the entire average itself.
Yeah. And this will, I think, exactly come 2 by 3 for all of them.
Yeah, for all four.
So it will basically come 2 by 3, 2 by 3 for all of them. So 2 by 3 into, uh, you have to also take the average over all the data points. Okay. So 2 by 3 plus 2 by 3 plus 2 by 3 plus 2 by 3 divided by 4. So it
Four.
will be again 2 by 3. Final answer would be 0.66. Okay.
And similarly for bias, if the question would have asked, then we would have just use the bias formula. The expected value of
Yeah.
f hat of x would be the same, and
Yeah.
just minus the
Expectation value of that would be same. It's just that in
yeah,
a bias we use true value.
yeah.
Okay. So what would have we used that? We just make use of these two things. One is y true and second is this. Just subtract off these two columns. That's all. And if they ask for the average, then just take the average there.
Okay, so
Okay. Now that is the case here that sometimes they do not ask the bias directly, they ask the squared bias so that the negative thing does not make any problem there.
okay. Can we just quickly go over what the bias here would be? Because I think it should be just 1, 0, -1, and 0. So it should be 0, right? If here we calculate it.
No, it will be 1 minus 2. Okay. So minus 1, then 3 minus 4 minus 1, 6 minus 6, 0, 8 minus 8, 0. So if you sum
Oh,
them up, you will get minus 2. If you are going to take the average over all the 4 data points, minus 2 by 4.
okay, okay.
Okay. So negative 0.5. Unless you do the squared bias calculation, then it will be just 0.5.
0.5, yeah.
Yeah. Any doubt here?
No, sir.
Okay. Which of the following are the regularization techniques? Dataset
For the
augmentation,
documentation.
activation function?
No.
No.
No,
Correct.
no activation function. L2 regularization,
Hmm.
adding noise to the inputs or outputs, and that's it.
Yeah,
Only three.
that's it. So one, option A, option C, and option D.
So just one thing here, that if we were to define what the purpose of an activation function it is, how would we define that theoretically?
Yeah, so activation function's purpose is to introduce non-linearity. Okay,
Non-linearity, okay.
yeah, that's all. So we basically take a non-linear differentiable function as our activation function. Okay, one more good question. I think this is like which of the following option here represent the correct ordering in terms of bias of the model. So
Yeah,
model
model A, option A would be correct. Option A.
A,
No, no, no. Last ACB.
yeah, this should be
Because
correct.
first one is simple model, so it has high bias,
Correct.
and C is
C
little
is
bit
in
complex.
between. Yeah,
Yeah.
model B is much more complex, so it will be very less bias. Okay. Which of the following is a common form of regularization that involved adding a penalty proportional to the square root of weights? Dropout L1, L2 batch normal and batch
L2,
machine.
L2 regularization, because that's the only one where
Yeah,
we score.
The L2,
yeah,
L2, L2. Yeah.
yeah. Correct. Okay, week seven. Now week seven. Main thing that you have to focus on is the activation functions. Okay. So two activation function we have already seen. Two. Have you seen 10H till now?
Yeah, 10H.
So one just quick overview. So we have the sigmoid that is 1 upon 1 plus e power minus x. Okay. Graphically, it looked like this. A is between 0 and 1. Okay. Use case, it's mostly used in the output layer. Okay. The cons of this sigmoid is it contains or it creates the problem of gradient vanishing. Okay. What does it mean by gradient vanishing? If your uh, input becomes very high value, okay, then if you see the sigmoid curve, here it will become flattened. Okay. So the gradients for very high magnitude value, whether you are in the positive direction or in the negative direction, it will become close to zero. Okay. So this creates the problem of gradient vanishing as the gradients will be very low or close to zero. So your model will not get trained properly. Okay. As the parameter will not get updated if the gradient is not there. Okay. Then we had tan h to overcome somewhat problem of sigmoid. Sigmoid has one more problem that it does not center the data set. Okay, the centering point for sigmoid is at 0.5 at the value of 0. So TANH technically overcome this problem that sigmoid does not center the data set. Okay, as a TANH graph goes like this, it stays between 1 and -1. Okay, and it center the data set as at the 0, the value of the TANH is 0. Okay, but TANH also has the problem of vanishing gradients, because if you see, the shape of TANH is also similar to the ReLU. Oh, sorry, not to the sigmoid. So when for any high magnitude value in the positive direction or in the negative direction, okay, the surface will become flat, gradient will become close to 0, model will not get updated. Same problem, vanishing gradient is. Okay. Next in the list is ReLU. Okay. ReLU is basically that max of 0, x. Okay. So for any positive input, it will behave like linear function. For any negative input, it will clamp it to 0. Okay. So this is the graphical representation of ReLU. The pros and cons of ReLU. Pros that it does not create that much big problem for vanishing gradient, at least for the positive part. But cons on the other end, for any negative input, if we once we got, then it will make the gradient directly to 0. Okay, so it creates the problem called as the dead neuron. Okay, now why we call it as dead neuron? Because for that particular neuron, the gradient will become 0. Okay, the gradient of ReLU is it will be 1 if the x is greater than 0. Okay, and it will be 0 if x is less than 0. This is the gradient for ReLU. So for any negative input, the gradient for the ReLU will be 0. Okay, so it clamps it to 0, so it creates the problem of dead neuron. So that's the cons of ReLU. And to overcome that, we have one more called as the leaky ReLU. Okay. What it does, kind of similar to the uh, ReLU, that for positive it will be just x. For the negative, it will be like, okay, so it is max of 0.01 comma x. Okay, so for the positive inputs, it's again behave like linear x. For the negative input, it would be 0.01 times x. Okay, so it will not clamp it to 0. It will still we will still be able to flow the gradients in that case. Okay. Now, one good thing that comes here is why is we have to make this specific as 0.01. So for that, we have this parametric ReLU. Okay, that is nothing but it will be x for positive, and then it will be kind of like some alpha times x. So max of alpha x comma x. Alpha would be like something you can choose as the hyperparameter. So it is parametric ReLU. Okay. Then we have elu, celu, gelu, but those are not much asked. That are not very much asked in the exam. Okay. So you can just read through them slides, but those are not usually asked in the exam. Okay. You can stick to these only. Okay. So let's start with question for week 7. So first question, that consider toy networks for the regression problem with input belongs to the real number and label also belongs to the real number. We have n minus 1 hidden layer here with one ReLU neuron in each layer. Okay, so each layer here, each neuron here is a ReLU neuron. That is the activation function used here is ReLU. Output layer also has one neuron that uses the linear activation. Linear activation means the kind of like same output will be passed. Ignore bias. H naught is x, y is hn. We have w1, w2 till wn minus 1, then wn, like this. Loss is half y hat minus y whole square. ReLU is defined as max of 0, z. X is starting with 1. True label is 0. Last subquestion is independent on the first two. First question. If all the weights are initialized to some k, where k is greater than 0, okay, and it is some constant, then what will be the value of y hat? All this?
So um, there are n minus one hidden layers, right? And then one output layer.
Yeah.
And that output neuron is also a ReLU neuron. Oh no, sorry, it's a
Now
linear.
output is
Linear.
linear. Okay. So what I will suggest you guys to
A n
do not
minus.
go with this n minus 1 n.
Yeah.
Start with your number. Create maybe a dummy structure with 3 neurons, okay, or 3 layers like that. In that
Okay.
you will be easily able to identify the pattern. Okay.
If k is positive, then output would be always, positive, not zero.
Sorry, can you
So,
repeat?
no, here what I am thinking, that k is positive, okay?
Yes,
So, and all hidden layers having
ReLU
ReLU
neuron.
as the activation function. So it would be
Yeah,
positive. That number
yeah,
is
correct.
nothing but k. And what is the function in the output? That is also ReLU.
It is linear.
Okay, linear.
Linear means identity activation. So as I said, start with like a small network of your own with let's say 3 hidden layers. Okay. In that you will be able to see how the forward pass is happening. Try that. Yeah, anyone got the answer?
Shouldn't it just be k?
Okay. Let's see.
No, no. It it would be k to the power n minus one.
Okay. K power n minus 1, K, two answer, but one of them was not in the option.
DB2 पर.
So let's start. Okay. We have to start from X multiplied with W1 multiplied with W2. And as I said, I'm going to take a small network as an example. So I'm taking 3 hidden layers. This is my first hidden layer. Okay. H1, this is my second hidden layer. This is my third hidden layer. And now I am output, giving the output here. Okay. So let how we are going to define our pass here. We'll be having this A1, H1, A2, H2, A3, H3. Okay. So take me here. This H3 will be Y hat. Okay. So 2 hidden layer. Okay. So A1 is what? W1X. X is what? 1. W1 is what? K. So A1 is just K. If you apply ReLU, because K is greater than 0, you are again going to get K only. So H1 is just K. Okay. Now this H1 will be fed as an input to the next neuron. So A2 is W2 H1. H1 was K. W2 is also K. H1 is also K. So it becomes K square. Because K is greater than 0, K square should also be greater than 0. Okay. And that's why the output of H2 after applying the ReLU here will also be K square only. Now comes the output part here. Okay, output A3 is defined as W3H2. W3 is K, H2 is K square. We will get K cube. Here you are going to apply identity function, but it doesn't matter. You are again going to get the same output H3, that is your y hat, as your K cube. Okay, so see how it was we were getting the answer based on the number of layers. We have two hidden layers, okay, and the weights are going from W1, W2, W3. So we've got K power 3. In the network given here, we had n minus 1 hidden layer. Weights were going from W1, W2 till Wn. So what will be the answer? K power n.
K power, and that's because even in the pre-activation of the output layer, it is still getting multiplied by.
Yeah, multiplied by one more
Yeah.
K. Okay. Now we are taking the derivative here of the loss function with respect to W1. Okay, so at part here, we evaluate it again the same condition that all the weights are initialized to K. Same condition, K is greater than 0. Okay. In other words, find this. Options are K power 2 minus 1, 0, K power 2n, and K power n minus 1. Okay. My loss function, if you forgot, this was my loss function. Okay. So we have already got our y hat to be K power n. We have given this loss function. This is the true label. Try finding the derivative of the loss function with respect to W1. Again, I'm going to say that start with this simple example. In that, try to find it, and you can just extend the idea in that case. Yeah, so anyone got the answer?
Just a minute.
Yeah, sure. Yeah, so shall we start now? Yeah. Otherwise, it's about to be 12. We can't stay for long. Yeah. So our loss function given to us was just half y minus y hat square. Okay. We will apply chain rule one at a time. The first gradient of loss function with respect to y hat. Okay. It will be y hat minus y. Okay. Now, as the true label for this data point was 0, and we got y hat as k power n, okay, we will get k power n here. Now things will start because now we are going to add the chain rule here. That is derivative of y hat with respect to uh, a and then derivative of a n with respect to h n minus 1 and so on. Okay, but of course, if I'm going to write it like this, then it becomes a little bit complicated to understand. So again, we will go back to this example. Okay, so I'll start with this example and see how it goes. So just copy paste that thing. Okay. Now here, if I define my forward equation, it was A1 was W1x, H1 was the ReLU of A1, A2 was W2H1, H2 was ReLU of A2, uh, A3 was W3H2, or H3 was identity function on A3. That was also my y hat. Okay. Then we come our loss function y comma y hat as half y hat minus y square. What we have to calculate is this quantity. How my W1 affect my loss function? How it affect? W1 affect A1, A1 affect H1, H1 affect A2, A2 affect H2, H2 affect A3, A3 affect y hat affect loss function. So go back to this 10. From y hat to A3, from A3 to H2, from H2 to A2, from A2 to H1, H1 to A1, A1 to W1. Okay. So gradient of loss function with respect to y hat derivative with respect to A3, A3 derivative with respect to H2, H2 derivative with respect to A2, A2 derivative with respect to H1, H1 derivative with respect to A1, and A1 derivative with respect to W1. Okay. So till now, is it clear? First of all, right.
Yes, sir, it's clear.
This part we have already calculated. It was y hat minus y. Okay. Now this part, derivative of y hat with respect to A3. If you look at this
That would
forward
be
equation, H3 is identity function on A3. So if we take the derivative, what it will be?
1.
1. Very good. Similarly, now derivative of A3 with respect to H2. Look at
That
this
would be
forward
2.
equation.
Yeah.
What it will be?
W3 or K.
W3. Okay, for now, just take it W3. This part, H2 derivative with respect to A2.
Again 1.
1, because we have the positive input here. Okay, that's why it will be 1. Otherwise, it can become 0 also. A2 derivative with respect to H1. What it will be?
W2.
W2. Again 1. Now, A1 derivative with respect to W1. What it will be?
X.
X. What you got? Y hat minus y was k power 3
Yeah.
into 1 into k into 1 into k into 1. X was also given as 1. Okay. In the question, where it is, X was also given as 1. Simplify it. k power 3 and k power 2. Now extend this idea
Yeah,
here.
so k to the power 2n minus 1 here.
Hmm. Okay. In this network, we have till n. So it will be k power n into k power n minus 1. It is k power 2n minus 1. Okay. Second option will be correct.
So in this, I did like a silly mistake here that instead of taking the derivative of the loss function to y minus y hat, I instead did like y hat minus y into y hat into 1 minus y hat.
Oh,
And
that is for sigmoid.
yeah, that's for sigmoid.
Hmm.
Yeah, I forgot that.
Hmm. Yeah. Okay. If all the steps, other steps were correct, then it was
Yeah,
fine.
rest was correct because I was getting something like k to the power 3 n minus 1 into 1 minus k to the power n because of that wrong loss gradient there.
That's okay. It's fine. Okay. So let's move on to the next sub question for this. It says that if wi is not equal to 0 for I between 1 and n, and y hat is 0, okay, and which of the following is true? So my prediction is 0, but my weight are not equal to 0, then which of the following here is true? That there exists some j for that wj has to be less than 0, wj has to be less than 0 for all the j, that is all the weight has to be less than 0, and there exists some j such that for it to be greater than 0.
First option could be correct that there exists some cases that
Correct.
WJ should be less than 0.
Yeah. What will happen if wj would be less than 0? How it makes it prediction to be 0?
Because we are I mean in activation function we are using ReLU,
Hmm.
so it will make 0
Yeah, correct.
if it's negative.
Correct. Okay. Yeah, so that's, yeah. So any doubt in this question? Okay. Now this is not very hard. What is the impact of using sigmoid activation function on the gradients when the input to the neuron is very large negative number?
Yeah, so the output approaches 0 and the gradient approaches 0.
Correct.
Yeah, first one would be correct.
And if the output is, sorry, if the input is very large positive number,
Then output approaches 1 and gradient still is 0.
correct. Question number 3. Consider a neural network given below with the 3 hidden layer and 1 output layer. Neurons in the network does not have any bias. Okay. The first and the second layer use the ReLU, and the neurons in the third layer use the sigmoid activation. Output layer use the softmax activation. And the ReLU is defined like this. Assume that all the elements in the weight matrix Wi are initialized with value 1, and the output of H2 is this. Which of the following weight matrix receive non-zero gradients here? So in all your calculation, treat any value less than 0.001 as 0 and greater than 0.99 as 1. So in the first and second hidden layer, we are using ReLU. In the third hidden layer, we use sigmoid. Fourth one use
So,
soft.
for W4, I think,
Okay. Why?
because in I mean third uh, I mean in third layer we are using which softmax.
No.
No.
In this
In
layer,
the
we are
output we are
sigmoid.
using. Yeah, in the output we are using softmax.
In the third, we are using sigmoid.
Yeah, in third we are using sigmoid.
So how does W4 becomes the answer? Okay, first note down the forward equations. Forward equations are A1 is W1X, H1 is ReLU on A1, Okay, A2 is W2H1, H2 is ReLU on A2, H3 is, sorry, not H3, A3 is W3H2, okay, H3 is sigmoid of A3, and A4 is W4 H3 and H4 yeah, softmax on A4. Okay. Now, one crucial information given to us is all the elements in the weight matrix are initialized with value 1. Okay. Now, what happens in that case? Take an example. If you have a matrix in which all the elements are just 1, if I multiply this matrix with this vector, what will be the output?
It would be the sum of all the elements, so it will be 12.
12, 12, 12.
Yeah.
Okay. So, what will happen here? A1 equal to W1 into X. You will get the output as sum of the elements in X, right?
Yeah.
Okay. You will apply ReLU on that. Okay. Whatever output you will get, something. Then W2 into H1. Again, you will get the output as sum of the elements in H1. You will apply ReLU on that. So far, okay. Here, W3H2. What will happen? You will get a sum of the output of some of the elements of H2. H2 is given to me. Okay. So the A3, I can find it out. A3 would be what? The sum of the elements,
Yeah.
what it is. 3 to 5,
5,
6,
6, 12.
12. 12, 12, 12, 12, 12, like this. Okay. Now I'm applying sigmoid on A3. So if you would calculate the sigmoid of 12, it will be close to 1. Okay. It will be very high value. So as in the question it is given, anything greater than 0.99, take it as 1. So sigmoid of 12 will be 1. Okay. So H3 is 1, 1, 1, 1, 1. And then this computation will be there and this computation will be there. Now, when you're going to backprop it, what will happen? The loss function here, if assuming we are using the cross entropy loss, okay, then the gradient of loss function with respect to A3 would be just this y hat minus y. Okay. Now, if you find the gradient of the, sorry, not with A3, with A4, if you find the gradient of loss function with respect to W4, it will be y hat minus y, okay, times H3 transpose. Okay. So, y hat minus y need not to be negative or need not to be 0. H3 also will not be 0 because H3 is just 1, 1, 1, 1. Okay. So W4 will not receive any 0 gradients. But if you now go more backward in the equation, okay, what will happen? The other or the previous sets will receive the gradient from this going forward from this H3 because the W3 have this H2 term. Oh, sorry, for the W3, it's affect A3. A3 is coming via this. Okay. But because the sigmoid values has become 1 here, okay, the gradients of sigmoid is basically sigmoid times 1 minus sigmoid. Okay. So it will make it 0. And if it will become 0, it will become 0 throughout the entire part. Okay. That is happening just because here we are using sigmoid and this is receiving very high positive number, which is making the gradient collapse to 0. And because it is becoming 0 here, it will become 0 throughout in all its past history also. Okay. For W4, it will not become because for the W4, the gradient is this. Okay. Which does not have any problem. Unless the y hat will become exactly equal to y, that's very rare case to happen. Okay, because you have to get the probability of 1 then. So is it clear why only W4 will receive non-zero gradients and other wet matrix will receive zero gradients?
Yes, sir.
Okay, so last week CNN, uh, I should have this before. So CNN, the main things that come from the CNN is the forward pass, backward pass, finding the output size and input size, and the number of parameters. Okay, so start with the uh, forward pass. We have the image. Okay, then in that image, what you are going to apply is called as filters. Okay, filters are nothing but your wet matrix only. But unlike ANN, okay, here my filter will be applied to like some portion of the image. So let's suppose I am just going to apply it here. Of course, it depends upon the size here. Like if this is a 5 cross 5 kind of image or matrix, okay, and this wet matrix for filter is 2 cross 2, okay, then it will first cover the 2 cross 2 block part. Okay, then I'm going to slide this. Okay, so first I'm going to apply here, then I'm going to slide it, and again I'm going to slide it till I hit the end. Then I will come downward. Okay, and this is how the filter is applied. But what happens when you apply this filter? We do the convolution operation. So that I mean, suppose my image contains these values. Okay, and my weight or my filter has this value 1, 2. For simplicity, let's just take this. Okay, then first I'm going to place this filter on this part. It will cover 2 cross 2 part. Okay, then I'm going to do the element wise multiplication. So 1 will be multiplied with this one, 2 will multiply with this one, 4 will multiply with this 0, 5 will multiply with this 0. Okay, element wise multiplication and do the sum of output. So it will be 1 plus 2 plus 0 plus 0. Whatever output I got, I will just write that in the output.
Sir, so convolution is just a fancy word of a weighted sum. That
Yeah, correct. Okay.
okay.
So now I'm going to apply it here. So I'm going to slide this. So now it will cover this part. Okay. So what it will be now just 5. Okay. Now this part is done. I'm going to now come downwards and cover this part now. After that, I'm going to slide it and cover this part now. Okay. So if I'm going to cover this part, I'm going to get 9. And later I slide on this part, I'm going to get 11. So this will be the output of my convolution. Okay. So that's the convolution operation. Now there's something called as max pooling operation. In that, what we do is you are going to take the maximum value in that window.
Yeah, yeah.
Yes.
Yeah, okay, sir. Okay.
Okay. So this was the convolution one. Now we have the max pool also. So in that, what we do if I'm doing the max pooling of 2 cross 2 filter, then in that 2 cross 2 region, I'm going to just extract the maximum value. So in that 2 cross 2, I have the maximum value of 4. In this 2 cross 2,
Five, right?
after, oh yeah, sorry, correct. And again, if I slide this, maximum value is 6. If I slide it downwards, it will be 8. If I slide it here, it will be 9. Okay. So this is the max pooling. Similarly to the max pooling, we have also the average pooling. Again, what will you going to do? In that window, you are going to just take the average of all the elements. Okay. Yeah. So these two things were there that were different: convolution operation and the max pooling. Usually we go with the max pooling, or in the question usually they ask with the max pooling only. But this is what you now, maybe not this one. Yeah, maybe we'll start with this one. Okay. So for a regression problem, consider an image of X of the size 4 cross 4 that is defined here through label Y that is passed through the toy convolution layer. So it has one convolution layer, single kernel. Kernel is this filter matrix that I'm going to apply now. Okay, followed by max pool operation. Ignore the bias. Okay. Now there's something called as stride and padding. Okay. So what does it mean by stride? Here, what I was doing is I was first applying my kernel here. Then I was just directly moving to next part. Okay. This is convolution operation with stride 1. In the case of stride 2, what will happen is I have to take one bigger matrix. Okay. And again, let's suppose I'm going with the 2 cross 2 kernels. Okay. Then what will happen? I'm going to first start with this. But if I set the stride to be 2, okay, then instead of starting with this, or next, I'm going to start with this. Okay. This is the stride of 2. You are going to skip 1 in that. Okay. So first with this, then with this, then in the vertical part also you are going to skip. So you're not going to start with this in the vertical part. You are going to start with this part. Okay. And similarly again this part. So this is the stride of 2. Similarly, if you you take the stride of 3, then you will be starting with this now. Okay. So that's the stride. Padding. Now if you are seeing, I have initially this 3 cross 3 image. My output was 2 cross 2 image. So output size reduced. But if you want that the output does not reduce, you generally apply padding. Padding is nothing but you add the zeros on each side, vertically, horizontally. Okay. So these zeros boundaries are get added. Okay. If I'm saying padding of 1, that means only one layer of zeros is added. If I'm saying padding of 2, that means two layer of zeros is added on both height and width wise. Okay, that's what defined as padding. Clear till now?
Yes, sir.
Okay, now going back to the question. So that's what they given, that S is the stride, P is the padding. So we have the stride of 1, padding is 0. K is 1, that means we are only using one filter here. Okay. F is the spatial extent of the kernel. F basically represent the size of the kernel. My kernel size is 3 cross 3, so that is my F. Okay.
So just one thing here, are kernels always a square matrix?
In our course, we will be only dealing with square kernels.
No, no, it's not always because in I mean practice question I saw kernel was not a square.
Yeah, but mostly if you are going to see the question, we will be dealing with the square kernels only. Okay.
Okay.
By there are very less chance that they ask question with rectangular kernel, but if you are asking in general, it can happen that you can have rectangular kernel also. Okay. Yeah. So first what they are asking is which of the following is the output produced by convolution followed by the ReLU layer. Okay. So if you apply this kernel on this image, just like we were doing it before, tell me what will be the output. First, this kernel will be applied to this part. What will be the output? See, it will be multiplied with 0. It will be multiplied with 1.
5, 3. So like the first row should be 5 and 3.
Four, 2, 1, and
2.
5 it should be there.
5. Yeah, 5. because there is two.
Okay. Mm. Okay. Now you, as because the stride is 1, you are just going to stride it by 1 and you are going to apply kernel on this part now. Apply it and tell me what will be the value.
3.
Okay, correct. Now you are going to slide it down as you have reached the end.
1, 2.
It should be 3 again, I think.
2, okay. Yeah, 3, sorry, yeah, 3. And then in
Okay,
the next one, 1,
it will be
2,
4.
4. Yeah.
Okay. Now, if you are going to apply ReLU on this, ReLU just apply element wise, same thing, right?
Convolution plus rally. Yeah.
Yeah. Okay. So this is what you are going to get.
Okay, so if there were any negative elements, like if, instead, suppose we had 5, negative 3, 3, and 4.
If yeah, then
So
it will
5,
become
0, 3, and 4. Yeah.
Negative would become 0.
yeah 5034.
Yeah.
Okay. Now our final y hat, how it is defined on the output of convolution plus ReLU, we are applying max pooling. So on this we will apply max pooling. F is 2. F is the filter size. So 2 cross 2. So entire thing will be covered in 1. Stride of 1, padding of 0.
So the output
What?
would be 5 here.
Very good. So y hat is 5. That is that. Okay. Now there's this backward pass also that we will come to later, but this is how you do the forward pass for the convolution. Is it clear?
Yeah.
Okay, and I hope the terminology is also clear. Now, few things, that is how you calculate the output shape. That if I just tell you that this is my input shape and this is the kernel that I am applying with this stride and padding, and this is the size of the kernel, and what will be my output shape and number of parameters. Okay, these are the general question that they generally ask. So starting with this question, that you have the input volume to be 64 cross 64 cross 8, where 8 is the depth or the number of channels. So just like we have the RGB image, in that we have the depth of 3. Okay, so in this we will be having the depth of 8. Okay, then we have the conv layer which has the 16 kernels. Now what we are doing in the convolution operation is, here we applied please mute, here we applied one kernel, we got this one output. Okay, in the convolution layer what we do is we apply many kernels. Okay, even in this one layer. So here the k was 1, we can apply k equal to 5, so that we will be applying 5 different kernels here. Okay, of course of the same size, that is if the first kernel is of size 3 cross 3, all the 5 kernels will be of size 3 cross 3. So I will be getting 5 different map here, output map. Okay, and what I'm going to do, I'm going to stack them together across depth. Okay, so on this convolution operation, I got this output as 2D because this is a matrix. So I will getting 5 such matrix and I'm going to stack them one after the another. So it's like building block, right? So on one block, I'm going to paste the another one. Okay, so the 5 kernel that I'm applying, the 5, that number is there, will become the depth of my output of this operation.
So is that a tensor now? That because we have
Yes,
5. Okay.
yeah, that is a tensor now. Okay, so that's what they are saying, that they are now applying 16 kernels, each of the special extent 5 cross 5. So 5 cross 5 is the size of the filter. Stride is 1, padding is 2.
So the first option is correct, sir.
Yeah. Let me write down the formula. The
N
formula is
minus k plus 2p upon s plus 1
F plus 2P by S. We are going to take the floor division plus 1.
plus 1.
Okay. So Wi is the input width. F is the filter size. P is the padding. S is the stride. And you add the plus 1. And you are going to do the floor division here. So with that, keep in mind, if you start Input width is 64, filter size is 5, padding is 2, so 2 into 2, stride is 1 plus 1. Okay, so 64 minus 5 is 59 plus 4 63 plus 1 64. Okay, so I'm going to get the 64 as height and 64 as width. What about depth? As I said, the depth will be equal to the number of kernels you are applying. So 64 cross 64 cross 60. Okay, yeah. Now, this question of find the number of parameters associated with the convolution layer.
Yeah, so it should be for the convolution layer. So
Hmm. You
8,
have 16 kernels, each of 5 cross 5.
and then there's also the depth of 8.
Yeah, depth also. Okay.
So 5,
So you
5,
will be having 5 cross 5 cross 8 multiplied with 16.
232. Yeah,
25 is at 200, 32,000.
yeah.
Okay. So 32,000 will be the, but these are weights. Okay. If they ask for the bias, then what you are going to add also? What should
Um,
I?
we just add 16 into 5, 16 into 8,
No, only 16 you are
only
going to
16.
add.
Okay.
Only 16. Reason is we add the bias on the final output. Okay.
Yeah.
So as on applying one kernel, this is the output that I got. So I'm just going to add bias here plus B. On each element, I'm going to add the same bias. So one bias is associated with one kernel. So as I have 16 kernels, there will be 16 bias. Okay. If bias is asked. Now, next question was if input volume becomes double at 128 cross 128 now, then would the number of parameter will change?
No,
No, right?
because
Oh,
it
Because
doesn't depend on input.
yeah, it
yeah.
only depends upon the filter size that you are using and the number of filters and the depth of the input. Okay, three things: the filter size, the number of kernels, and the depth of the input. But depth of the input is constant. Other two things also not changed, so parameter will not change. Okay, any doubt? Okay, so the main parts are clear: how you do the forward pass, how you do the calculation of max pooling and all. Okay, one note here: max pooling layer or average pooling layer. Any pooling layer does not have any parameter, because what you are doing in the max pooling, you are just directly calculating the max value here, right? You do not need any weights here to calculate for it. Okay, so any type of pooling layer, whether it is max pooling or average pooling, does not introduce any new parameter. Okay, so only the backward pass is remaining now from week 8. I think, yeah, output size 10, parameters 10, forward pass 10. Okay, so
So only these kinds of questions would be asked from week 8, just the size
yeah,
and parameter now count.
yeah, like these are the general question that generally asked.
Okay.
Okay, now of course in that how they mix up new things, it depends on them. So for the backprop, how you do is you have the image, you apply kernel, you will get the output of convolution, you apply ReLU, you get the output of ReLU, you apply max pool. Okay, then you can flatten the output. So as after applying max pool, if the output was like 2 cross 2, you can flatten it, and then you can do your simple ANN thing. Okay, this is how a general architecture of CNN will look like. Okay, so it's like you have your input matrix X or input image X. You will do the convolution operation. You will get something called as A1. You will do the ReLU. You will get H1. You will apply max pooling. Let's suppose you get M1. You can flatten it. You will get F1. Okay. Then the simple ANN thing will start from here. You will apply multiply it with weights and bias. And A2. You can apply sigmoid. You will get H2 as bias. Okay. So yeah, the forward pass we have already done that. If this is your X matrix and you apply your kernel on this, okay, then you will get this forward pass equation. Now we have to start from the backward equation. Okay, how this back propagation will start. So assuming that I am using the loss function as cross entropy, okay, the initial part will be same because in the outermost part here, we are doing the ANN thing that we were doing. Okay, so gradient of loss function with respect to A2, okay, this one before applying the sigmoid, okay, will be just y hat minus y. Okay, now from A2, if I want to calculate the gradient with respect to W2, then I have to look at the equation, how it was. A2 was W2 times F1, okay, like W2 times F1 plus B2. On that, we got the A2, okay. So it will be just F1 transpose. This is also same thing that we were there in the ANN again, okay. For B2, it is same. I would like to come with this part, the flattening part. How you take the derivative when you flatten the equation, okay. So derivative of flattening is just the reshaping, okay. So if after flattening, like if you had this, sorry, one minute, yeah. So if you had this matrix, let's suppose of 2 cross 2, and I'm going to flatten it to a 4 cross 1 vector. The derivative of this is you're just going to reshape it to back to the same size, 2 cross 2. But here, what you will be having is the derivative vector. Okay. So this derivation that you are going to get, the gradient of the loss function with respect to F1, you are going to get, or you are going to reshape this back to the same size that you were there before flattening. Okay. So this was for the flattening case. Then for the pooling case, okay, how you find the derivative of with respect to pooling layer. Okay. So suppose you will have this matrix, you had this matrix and you were applying max pooling on this with stride of 2 and kernel size is 2. Then you are first going to focus on this part, then later on this part, then later on this part, and then later on this part. This is how you are going to get the max pooling output. Okay. Its derivative is only the place where from which we got the maximum value. The derivative would be 1. Okay. So what were these places? This one, this one, this one, and this one. So only in those places the derivative would be 1. Other place it would be 0. Okay. So it will be like a matrix of 0, 0, 0, 0, 0, 1, 1, 0. Okay. So this will be the derivative of this max pooling output with respect to its input. Okay. Now, if of course you have to do the whole chain computation and then you are going to get some. But remember, for the max pooling, only the place from where you got the maximum value, only at those place it will be 1, other place it will be 0. Then comes the final part, the kernel one. Okay, the convolution operation. Okay, so back propagation in convolution layer is defined as if you have the metric X, you are applying the convolution with kernel K and you are getting A1. Okay, so you have this X, you have this K. Okay, now this part, uh, you got this after applying the kernel. Okay, so A11 was W11 into X11, W12 into X12, W21 into X21, W22 into X22. Okay, this was what I have written here. Similarly, A12, A21, and A22. Okay. Now, till now, what would have happened that through back propagation using chain rule, you must have gotten something that is the gradient of the loss function with respect to A. Okay. Now you have to find the gradient of loss function with respect to k. K is my kernel. Okay, so it would be using chain rule, gradient of loss function with respect to a into gradient of a with respect to k. But this part we have to find. What is this value? So for that, we are going to calculate this. That for each weight here, we take the derivative. Okay, then again using chain rule, it will be gradient of loss function with respect to a11 multiplied by a11 derivative with respect to w11 plus a12 derivative with respect to w12 and so on. Okay. This part will come from this matrix derivative and the a11 with respect to w11. So in the a11 equation, w11 is here, it's multiplied with x11. So that will come. For a12, it is multiplied with x12, that is here. Okay, then x21 and x22. Okay, so in a nutshell, if you are not able to remember this thing, okay, and then what you actually get is that gradient of the loss function with respect to kernel is nothing but that whatever the derivative matrix that you are going to get before going through the derivative part of the kernel operation, okay, it will be the convolution operation of that derivative matrix with respect to the input image. Now I know this won't be able to go into your head if you are not going to solve this question. So this will be the last question that we'll be solving for today. Okay. In that, what we'll be doing is the output that we got, y hat. Okay, we are going to back propagate it with this loss function and find the derivative of w13. Okay. So if I note it down, this operation that we had here, we had the x, we apply our convolution operation, okay, with w. Okay, we got something, let's suppose we call it as a. Okay, then we apply the max pooling operation. Okay, and we got y hat. Of course, in between, let's suppose you can add one more for ReLU part also. So h. Okay, this was the entire flow for this network given here. So let's start finding the derivative first with respect to y hat. Okay, given this as the loss function, this we have already seen many times, it is y hat minus y. Okay, now go back to the chain. Next is this, the max pooling derivative. We just now saw the max pooling derivative is nothing but only the place where we got the max value. At that place it will be 1, other place it will be 0. Going back to the case, we had this matrix on which we apply the max pooling. Here the maximum value was 1 here. So the derivative of y hat with respect to h, that is the derivative of the max pooling operation, is this 1 0 0 0. Okay, only the place from where we got the maximum value, it will be 1, other place 0. Okay, going back from h to a, it is the ReLU operation. Okay, now ReLU, same thing follow. Okay, if it was greater than 0, then 1. If it is less than 0, 0. Okay, on this image when we apply ReLU, or on this output when we apply ReLU, it was greater than 0 everywhere. Okay, so what we are going to get, gradient of h with respect to a is this 1 1 1 1 everywhere. Okay, it will be a matrix here. Now final part, gradient of a with respect to w. Okay, because this is what we have to find it out. Okay, that part is now, before going to that, we now saw that here where it is this, that this part where it is gradient of loss function with respect to my kernel weight is nothing but if I do the convolution operation with respect to whatever I have got so far. Okay, so this gradient of loss with respect to a1. Okay, this is nothing but the multiplication of these three, because till now we have got this much. Okay, so this multiplication has to be in element wise. Okay, so let's do that. Okay, so gradient of loss function with respect to A is y hat minus y 1 0 0 0 1 1 1 1. Y hat is 5 and y is 4. Okay, it is given here. So 5 minus 4 1 0 0 0 1 1 1 1. You are going to get 1 0 0 0. Okay. Now what you are going to do, if you want to find the derivative of loss function with respect to my kernel weight, I am going to take this matrix as a kernel and apply it on my input image. And the output that I am going to get will be the derivative of my loss function with respect to the kernel filter that I applied. Okay. So I'm going to, just like we were doing the normal convolution operation, now I will treat this matrix as the kernel and apply it on this. Okay. So the matrix that I got was this. Okay. On this, if I apply it, then what in the question they asked is W13, this part. Okay. So tell me what will be the output if I do this convolution operation here.
We are supposed to do the convolution operation 1000 on that.
Yeah, on this input image.
So it
What
should
it will
be
be?
102 and then 011 and 020.
Okay. So this is the gradient of loss function with respect to W. Okay. And they were asking for W13, so it will be 2 here. Okay. So three things that you have to care about here. Derivative of the flattening operation is basically just the reshaping. Derivative of the pooling, max pooling specifically, just it will be 1 from where we got the maximum value 0 everywhere. And the derivative of the convolution is nothing but the you have to do the convolution operation again. Okay, with the derivative matrix that you got so far. Okay, yeah. So is this clear?
Yes, sir.
Sort of.
Yes. So it won't go in one time, I would say. So maybe try doing a little bit more practice on this with some more questions. Okay. So as the time is up, but there's nothing more new in the week 8. Okay. Generally, the question will be around these parts only. Okay. So just try practicing on them. And I will just suggest maybe 1 minute. Just suggest. Mm, condition. Yeah, I will share it. 1 minute.
So where would the PDFs be available?
I will share it now in the class. Okay, and I'll share it with uh, Kaziranga house. Okay, they might either upload in the events or something. Okay.
I'm actually not from the Kaziranga house. I'm from Saranda. So,
Yeah, I will share this one here.
okay.
Yes, so you can look at this playlist here. Okay, for the CNN backpropagation mode, underestimate mode, and for this one PDF I will be sharing. Yeah. Yeah, and this is the notes for today. Okay. So both have shared. You can look at the playlist more to understand the CNN backpropagation if you want, and I will also share the notes. All for today's session. Yeah. Okay, so any doubt? Anyone? So can you share those handwritten notes full? So okay, those one minute. For which week you want? Okay. Yeah. So and it will take a little bit more time. Yeah.
Well, okay, I guess it looks like the session has actually concluded. Thank you, everyone, and a big thanks to you, Pulkit, for joining and taking out your valuable time and conveying and explaining all such concepts to the students and to me as well, because I have also taken learning this term. Thank you so much for that. With that, I guess I can close the recording and streaming of this session. So I'll be doing that, and others, you can find the recording of this video on YouTube if you want to refer it once again. We'll share all the notes and everything in the comment section of this video, so that would be helpful for all of us. So I'll be closing the streaming and recording. Thanks a lot for joining in.
Yeah. Thank you all for joining. Uh, these are the notes that were used in the today's session.